Recording. So when we last left off, we finished our discussion of the periodic trends associated with atomic radius and ionic radius. Now we're going to look at periodic trends for ionization energy. Now let's talk a little bit about the definition of ionization energy. It's the energy required to remove an electron from an atom in the gaseous state, in the gas phase. For example, going from sodium gas to sodium plus. Note, this is in the gas phase, and this will come up later when we start to discuss the Born-Haber cycle. Now, the ionization energy is dependent on the energy of an electron and the nuclear charge. In general, it always costs energy to remove an electron. Electrons are stabilized by the nucleus, and as a result, it takes energy to pull that electron away from that stabilizing interaction. So let's now look at a graph of ionization energy as a function of atomic number. So I'm going to label the graph with different n values. So we have n equals 1, n equals 2, n equals 3, n equals 4, and n is equal to 5. And my question to all of you is, as we move down a column, as we move down a group in the periodic table, what happens to our ionization energy? Does it increase or decrease as we move down a column? And don't be shy to type your responses in the chat. So looking at this graph of ionization energy as a function of atomic number, as we go down the periodic table, what happens to our ionization energy? Does it increase or decrease? It decreases, exactly right. So as you move down a group or column, just one moment. So as you move down a group or column in the periodic table, ionization energy decreases. So what this is meaning is that it takes less energy overall to remove electrons in an orbital that is farther from the nucleus. And the reason for that is electrons in larger outermost orbitals are high in energy and are less attracted to the nucleus. And as a result, these electrons are easier to remove. Okay, so looking at this from a more tangible standpoint, if we compare sodium and potassium, sodium has a larger ionization energy because it is higher up on the periodic table. Likewise, potassium has a lower ionization energy because it has a larger orbital size, and as a result, the electron in potassium is higher in energy and easier to remove. Now let's keep looking at our graph, and let's try to conclude what happens as we move to the right across the periodic table. So as we move to the right across a row, as we move to the right across a periodic table, what happens to our ionization energy? Does it increase or decrease as we move to the right on the periodic table? So as we move to the right across a row, what happens to our ionization energy in this graph? So going from lithium to neon, is our ionization energy increasing or decreasing? So just looking at a single subsection. So going from lithium to neon, as we move right across a row, our ionization energy increases. Okay, so let's note that. As you move right across a row or period, your ionization energy increases. So for example, fluorine, which is farther to the right in a row compared to carbon, fluorine has a larger ionization energy than carbon. Okay, let's keep going now. So in terms of some baseline rules, ionization energy always increases with effective nuclear charge. The smaller your atomic radius, the closer the electron is held to the nucleus, and the stronger the attractive interaction between the electron and the nucleus. Ionization energy decreases dramatically with increasing orbital size and increasing orbital energy. So the way that I like to think of ionization energy is I like to draw an arrow going up and to the right. This is ionization energy increasing. So this is just a nice little mnemonic to help you remember. Now, for noble gases, as a full shell is very relatively stable, the ionization energy is typically very large for noble gas configurations. Okay. So comparing each pair of elements, let's try to identify which element has the largest ionization energy. So let's look at an example comparing fluorine and bromine. So fluorine is N is equal to 2, and bromine is N is equal to 4. So comparing the orbital size, fluorine is smaller. So fluorine is smaller. And as a result, fluorine has a larger ionization energy. Okay, let's look at another example, comparing potassium and bromine. So bromine is farther to the right on the periodic table. In other words, bromine has a greater effective nuclear charge, and as a result, bromine has a larger ionization energy. Okay, so with these two representative examples established, I'd like you to identify for the following two pairs of atoms which element would have the largest ionization energy. And we'll discuss this example in about 4 minutes. And the responses I see in the chat look great so far. And we'll discuss this example in about 2 to 3 minutes. To answer the question in the chat, you're thinking of electronegativity, and electronegativity and ionization energy often follow similar trends, but they have subtle distinctions in terms of which atoms, there are subtle distinctions associated with ionization energy that we're going to discuss momentarily. You can use it as a heuristic, but it's not 100% correct to correlate electronegativity solely with increasing ionization energy. But the trends match up in most cases. And we'll discuss this example in another minute. Okay, so let's discuss this example. So comparing carbon and fluorine. Fluorine is farther to the right on the periodic table, and as a result, fluorine has a greater nuclear charge, and as a result, fluorine has a larger ionization energy. Comparing lithium and sodium, lithium is N equals 2, sodium is N equals 3. Okay. So now, as a result, lithium is smaller, has a smaller outermost orbital. As a result, those outermost electrons experience a greater attractive interaction with the nucleus. And as a result, lithium has a larger ionization energy. Does this make sense to everyone so far? Okay, so let's continue on now and let's do some case studies. This is where we're going to apply our ability to draw orbital box diagrams. So to go back to answer the question in the chat, lithium is smaller because its outermost orbital has a smaller N value, which implies the orbital is closer to the nucleus. Because the lithium's outermost electrons are closer to the nucleus, they experience a greater attractive interaction, they're lower in energy, and as a result, they're harder to remove. Does that make sense? Okay, perfect. So let's look at some case studies now, since we noticed some odd sections in our ionization energy chart where the ionization energy just almost appears to randomly drop. However, these drops are consistent across each row, which means something deeper is likely going on with the energy associated with removing an electron from certain elements. Okay, so let's try to explain. Let's first try to explain the drop in ionization energy for group 3A and 6A elements. So to do that, we're going to look at a series of charts. First, we're going to look at oxygen, nitrogen, and oxygen plus. Note, nitrogen and oxygen plus are isoelectronic. So let's try to answer the question, why is the ionization of oxygen to oxygen plus, this ionization is relatively easy compared to nitrogen? Why is it easier to ionize oxygen versus nitrogen? Well, looking at oxygen, what immediately stands out to us? In oxygen, what do we have that raises the energy of our electrons? What do we have looking at our orbital box diagram? So the electrons in oxygen, we have a set of electrons that are what? So what's special about oxygen compared to nitrogen? We've drawn out these orbital box diagrams. We have them side by side. What is the major difference? In oxygen, what do we have that nitrogen does not? Has a set of paired electrons, exactly right. And these paired electrons are relatively high energy electrons that are easier to remove. So if we compare oxygen and nitrogen, it is uncharacteristically easier to ionize oxygen compared to nitrogen because during ionization, you're removing a high energy paired electron. Does that make sense? So just to recap, the 5A ionization energy is greater than the 6A ionization energy. That's because it costs energy to pair electrons, and as a result, it costs less energy to remove a paired electron to ionize a 6A element. Note, this ionization energy is not small, but it's smaller than nitrogen, which is unusual because oxygen certainly has more protons. Does this make sense? Does the reason behind this exception make sense? In general, it's easier to remove. We have lower ionization energies when we're removing high energy electrons, such as electrons that are paired, or, as we'll see in a moment, electrons that are in high energy orbitals. Can I get some responses in the chat that everyone's comfortable about this idea? Perfect. We'll talk more about that. In terms of the electrons paired in the s orbital, there's another effect going on that mitigates this pairing energy penalty. We'll talk about that momentarily. Okay, so let's look at another effect. So let's compare boron and beryllium. In other words, beryllium is isoelectronic with boron plus. So why is it so easy to ionize boron relative to beryllium? Well, if we look at boron, once again, we see we have an electron in a high energy 2p orbital. Because we have this lone electron sitting in a relatively high energy orbital, because remember, if we think about the relative energy of our s and our p orbitals, the p orbitals are higher in energy. So we have this high energy electron, and it's easier to remove this high energy electron. As a result, it's quite facile to ionize a 3A element compared to a 2A element. And the reason for that, it's easy to remove the high energy electron sitting in our 2p orbital. Does this make sense to everyone? Any questions on this example? Okay, so let's keep going now and let's look at some other ionization energy case studies. So we also see this dramatic jump in ionization energy in the transition metals and between our 1A and 2A elements. So to answer the question in the chat once again, so ionization energy in general increases as you move to the right. There are exceptions associated, for example, with as you move from the 2A to 3A elements, because for the 3A elements, they're actually easier to ionize because you have a high energy electron that's easier to remove than usual. So even though in general, as you move to the right on the periodic table, your ionization energy increases, there are some exceptions. And that's why we're talking about these exceptions, and we're justifying these exceptions using these orbital box diagrams. Perfect. I'm glad it makes sense. Okay, so let's look at a few more interesting cases where our ionization energy undergoes a pretty dramatic change as we move across the periodic table. Well, so this is where we have to bring up quantum effects, and quite simply, it's this idea that half-filled or fully filled subshells are more stable than other configurations. So this is due to both symmetry arguments and the fact that we have degenerate electrons. So this is partially why D5 and D10 configurations are especially stable. Now, the reason why this is important is a corollary to this idea is that electrons are more difficult to remove from half-filled or fully filled subshells. So as a result, S2, S2P3, and S2P6 configurations are relatively hard to ionize because you lose some of this stabilization from having a half-filled or completely filled shell or subshell. Okay. Let's now take ionization energy and show how we can use ionization energy to assign the identity of an unknown element. So what we've been looking at so far is first ionization, which is the removal of our first electron. But there are also second, third, fourth, etc. ionization energies. So we can successively ionize our atom, successively removing more and more electrons. So the first ionization, we remove our first electron, second, the second electron, third, the third electron, and so forth. Now, ionization energy increases for successive ionization because as you continue to remove electrons, you have a relatively large nuclear charge compared to a relatively small number of electrons. And as a result, removing an electron from a cationic species with a large nuclear charge is difficult. And the larger the cation charge, the more protons that are found in that cation's nucleus, the larger the ionization energy. Now, there comes a point where you'll see this almost catastrophic rise in ionization energy, and that occurs when one attempts to ionize a noble gas configuration. So we can use these ionization energies to identify elements. So let's look at an example. So as we can see very clearly in this graph, the ionization energy increases quite dramatically as you move to the right on the periodic table. Okay. Now notice for sodium, the first ionization energy is not very large, but the second ionization energy for sodium is quite large. So let's draw that out. The first ionization for sodium, we're going from sodium to sodium plus an electron. In other words, we're going from neon 3s1 to neon. Would someone like to explain what's so problematic about the second ionization energy? We're going from, just writing it out, we're going from sodium plus to sodium 2 plus. So we're going from helium two S2 2p6 to helium 2s2 2p5. And what's so problematic about, why is this second ionization energy so large? What are we trying to ionize in our second ionization energy? That's part of it, but what's so special about the configuration of sodium plus? What's so special about the configuration for sodium plus? It's yes, it has the same configuration as neon. And what configuration is neon? It's what kind of electron configuration? What kind of configuration is that? Yes, yep, it's a noble gas configuration. And noble gas configurations, or full shells, are difficult to ionize and have very large ionization energies. This is especially true if you're ionizing or attempting to further ionize an ion with a noble gas configuration. It's the same reason why, for example, the third ionization energy for magnesium is problematic. So going from magnesium to magnesium plus, we're going from neon 3s1 to neon 3s2 to neon 3s1. No problem so far. Magnesium plus to magnesium 2 plus. We're going from neon 3s1 to neon. And where the wheels fall off is when we try to go from magnesium 2 plus to magnesium 3 plus. We're going from helium 2s2 2p6 to helium 2s2 2p5. And this is where the wheels fall off because we're trying to ionize a noble gas configuration. And that results in a very large increase in ionization energy. So by looking at our first, second, and third ionization energies, we can, through deduction, identify the highest ionization energy as the ionization, or not the necessarily largest, but the ionization energy with the largest increase as the ionization energy associated with ionizing your noble gas configuration. Once you know the noble gas configuration, you can work backwards and assign the identity of your element. So let me show how that works. So we're given this information. We have a period 3 unknown element that has the following ionization energies: first, second, third. Okay, so I'm just going to write out the equations. So for our first ionization energy, we're going from our ion X to X plus an electron. For second ionization energy, we're going to X plus to X2 plus an electron. Finally, for the third ionization, we're going from X2 plus to X3 plus. And the third ionization energy is our largest. So my question is, looking at this problem, which ionization corresponds to ionizing a noble gas configuration? Which ionization has the largest ionization energy? The third ionization, exactly right. So then, the noble gas configuration that we're ionizing is X2 plus. So X2 plus has a noble gas configuration. Since we know that we have a period 3 element, we look in the periodic table and we find the preceding noble gas. In this case, the preceding noble gas is neon. So we are able to deduce that X2 plus has a configuration of neon. And now if we want to go from X2 plus to X, we simply add 2 electrons. And those added electrons, if we look at our periodic table, will go first in our 3s orbital, and our second electron will also go in the 3s orbital. So that in turn gives us the configuration neon 3s2, which matches the identity of magnesium. Just to show this addition idea a little more tangibly, so we've assigned the configuration. So this is our inner core of neon. Now, if we need to add 2 electrons, so here's our inner core for neon. If we need to add an additional 2 electrons, we would have to place them in our 3s orbital. Does this idea make sense of utilizing ionization energy to assign the identity of an element? So let's keep going now, and let's try to work on this example on our own. You're given a period 2 unknown element has the following ionization energies, and I'd like you to identify the following element. And we'll discuss this example momentarily. And the assignment I see in the chat looks reasonable so far. And we'll discuss this example in another 1.5 to 2 minutes. And let's try to get a few more assignments in the chat or some questions in the chat just to make sure everyone is following along and any questions that you have can be addressed. So to answer the question in the chat, we've discussed this idea that noble gases are very, very hard to ionize. So when you go from ionizing a non-noble gas configuration to when you ionize your noble gas configuration, the noble gas configuration will cost disproportionately more energy to ionize, and as a result, you'll see the largest jump in ionization energy. Does that make sense? Did that address the question in the chat? Okay, so let's discuss this example. So I'm going to write out my first, second, and third ionizations. It's always important to connect things back to a chemical equation. It's the most tangible thing that we have in terms of helping to understand reactions and reactivity. So looking at our ionization energies, where do we see the largest jump? Where do we see the largest increase in ionization energy? Where do we see the largest jump? Not the largest value, the largest increase. Where do we see the largest increase in ionization? The first to second. So our second ionization is when we're ionizing our noble gas configuration, because that's where we see the most dramatic increase in ionization energy. Does that make sense? So it's not the largest value, it's the largest increase in ionization energy that indicates you're starting to ionize a noble gas configuration. Okay, so now that we've identified our second ionization is when we're ionizing our noble gas configuration, we know X plus has a noble gas configuration. Since we're in the second row, when we lost electrons, our noble gas, our preceding noble gas is helium. Okay, so we know X plus has a noble gas configuration of helium, and as a result, X, if we add an electron, would have a configuration of helium 2s1. And that in turn provides a perfect match to lithium. Does that make sense to everyone? Any questions on this example? So it's not just the largest ionization, but it's not just the largest ionization energy, but the largest change in the ionization energy. Any questions on this example? If not, let's keep going and let's look at the exact opposite of ionization energy, in this case, which is electron affinity. So electron affinity is the energy released or absorbed when an electron is added to an atom in the gas phase. Now, in general, adding an electron to an atom typically releases energy as electrons are stabilized by the nuclear charge. Now, if we look at this trend for electron affinity, which is negative, it's a little bit more muddled. There's a little bit more nuance here. So let's look at our main points. So if we look at n equals 2, n equals 4, n equals 5, as you move down a column. As you move down the periodic table, what is happening to the value of our electron affinity? What is happening to the value of our electron affinity? Is it increasing or decreasing? Yep, our electron affinity decreases. So as you move down a group or column, electron affinity decreases. Now, further, looking at what happens as we move right across the periodic table. So looking at just a snapshot in one row of the periodic table, as we move to the right across the periodic table, what happens to our electron affinity? Does it increase or decrease? Increase, exactly right. As you move right across a row or period, your electron affinity increases. This is why, for example, fluorine has a larger electron affinity than carbon. Fluorine is farther to the right, has more protons, greater nuclear charge, and in turn, it's more readily able to stabilize an added electron. Okay, so everything seems to match. It's almost the exact opposite of, actually, it very, very closely correlates with the trends that we observed for ionization energy. So, just as a summary, as you move down a group or column, electron affinity decreases. As you move right across a row or period, electron affinity increases. So again, if you wanted to think about increasing electron affinity, I like to draw an arrow pointing up and to the right. So here's a table with common electron affinities. And again, we begin to see some very clear exceptions to these general rules. So let's talk about them. So electron affinity becomes more negative, larger, if you minimize repulsive interactions between electrons. So the electrons have more space to occupy without engaging in repulsive interactions, or you're minimizing the pairing of electrons. So if adding an electron would require that you add electrons to high energy orbitals or pair electrons, it is less favorable for that atom to gain an electron, unless you get a full subshell, of course. So let's look at some exceptions in electron affinity. And let's first look again at the 2A and 3A elements and the 5A and 6A elements. These are always going to be problematic, as we've discussed in ionization energy. These are the cases where we run into pairing effects and orbital energy issues. So let's talk a little bit of why 2A and 5A elements have small electron affinities. Uncharacteristically small electron affinities, for that matter. So half-filled or fully filled subshells are generally more stable, right? The S2, S2P3, S2P6 configurations are relatively stable. This is due to symmetry arguments, or this idea that your electrons are all degenerate, identical in energy, and that imparts a relative amount of stability to your system. Now, gaining electrons is more favorable if you generate a half-filled or fully filled subshell. Okay. Well, if we think about the difference between a 4A and a 5A element, when carbon, which is a 4A element, attempts to gain an electron. So this is the electron affinity process for carbon. That electron is going into an empty orbital and a half-filled orbital is generated. So this is a relatively favorable process. Now, if we compare this idea to something like nitrogen, so when nitrogen tries to pick up an electron, where does that electron have to go? Is that electron going into an empty or an already half full orbital? So when we try to add an electron to nitrogen, what do we have to do to the added electron? So we're adding an electron to nitrogen. This process is not particularly favorable for the first ionization. And why is that? What do we have to do to the added electron? What is happening to our added electron? It has to be paired, exactly right. So, and this is really important because in order to pair electrons, this pairing costs energy. So for the first ionization for nitrogen, if nitrogen gains an electron, the electron is paired, and this pairing process is not favorable. That's why nitrogen, for its first ionization energy, it has a relatively small first ionization energy. Does that make sense? So just like it's easy to remove a paired electron, it's not very favorable to add an electron if you have to pair it. Okay, so let's keep going now, and let's look at another example, and let's explain why 1A elements have larger electron affinities than 3A elements. So the electron affinity is generally larger for 1A elements compared to 2A elements. So let's start by looking at 2A elements. So if we wanted to add an electron, to beryllium, what orbital will we have to place that electron in? Are we placing it in a low energy s orbital or a high energy p orbital? Just remembering that s orbitals are lower in energy than p orbitals. So where is our new electron going? Where do we have to place our new electron? What orbital is our new electron ending up in? Yep, we're placing this new electron in a high energy p orbital. So when we're adding this electron as the result of ionizing beryllium and gaining an electron, adding this electron places it in a high energy orbital. As a result, it is less favorable for beryllium to gain an electron. And as a result, that's why we see a characteristically small electron affinity for beryllium. Does that idea make sense to everyone? Just like it was easy to remove an electron from a high energy p orbital, it is conversely difficult to add an electron if you're placing it in a higher energy p orbital. Any questions on this idea? Okay, so now let's look and let's try to explain why do 1A elements have an uncharacteristically large electron affinity? Well, if we think about what happens when we add an electron, that added electron is going into an s orbital, sure. And at the end of this process, after we've gained our electron, what do we see is true about this s orbital? Is it full, half full? What's up with this s orbital? Is it full or half full? It's full. So this full s orbital is relatively stable. And as a result, it is more favorable than usual for 1A elements such as lithium to gain an electron and undergo ionization. So this is why 1A elements such as lithium have larger electron affinities than 3A elements such as boron. Okay, so we've explained and we've summarized the reason behind these exceptions in electron affinity. Any questions so far? So let's look at another exception which occurs when we move down the periodic table. So let's try to explain what's going on with our electron affinity. Why is our electron affinity increasing as we go from n equals 3 to n equals 2? Well, let's start off with some basic premises. So electron affinity becomes more negative as repulsive interactions between electrons are minimized. So electron affinity increases as you move from n equals 2 to n equals 3. This is one exception to our general rule. And the reason for that is that if we compare a 3p orbital to a 2p orbital, the 3p orbital is substantially larger. So here's our 2p orbital, here's our 3p orbital. And as a result, if we have electrons in that orbital, the 3p orbitals, because they're larger orbitals, the electrons in turn have more space to occupy and generally experience a smaller amount of repulsive interactions. Thus, even though the electrons in this 3p orbital experience a slightly decreased amount of interaction and stabilization with the nuclear charge, adding an electron to the 3p orbital is often more favorable than adding an electron to the closely packed 2p orbital because you're minimizing repulsive interactions. Now, this exception is not general. When you move from n equals 3 to n equals 4, then orbital size and how readily your electrons in your orbital can interact with the nucleus plays a much bigger role. So when you start to go to a 4p orbital, so just as a comparison, so this is our 3p orbital. When we move to something like a 4p orbital, the electrons experience less stabilization by the nuclear charge, And that in turn leads to a smaller electron affinity. So this is why adding an electron to a 4p orbital or an n equals 4 orbital is less favorable than adding an electron to a 3p orbital. Does this exception and trend make sense? Any questions on this example? So let's talk about a summary for electron affinity, and let's try to apply these rules to rank species in order of increasing electron affinity. So first, electron affinity becomes more negative as you move right across a row. Electron affinity also becomes more negative as you move from n equals 2 to n equals 3. But past n equals 3, electron affinity becomes smaller as your n increases. As a general rule, combining what we've discussed, the electron affinity can be ranked as follows for each of our main group elements. So let's take a moment and let's rank the following atoms in order of increasing electron affinity. So let's take about 3 to 4 minutes, and I'd like to see a few rankings in the chat, and then we'll discuss momentarily. And if you have any questions, don't be shy to type them in the chat or unmute and ask your questions verbally. I'd like to see a few proposed rankings in the chat before we discuss in 1.5 to 2 minutes. Yes, in general, electron affinity increases as you move to the right on the periodic table. Just make sure you're accounting for exceptions. And we'll discuss this example in about another minute. And the responses I see in the chat look great so far. Okay, so let's discuss this example. So generally, electron affinity increases as you move to the right on the periodic table. However, we need to know some exceptions. The 2A ionization, the 2A electron affinity is less than the 3A electron affinity, and the 1A electron affinity is generally greater than the 3A electron affinity. Remember how we discussed in this first case this idea that placing an electron in a high energy p orbital is not favorable. In the second case, generating a completely full subshell is especially favorable. 5A elements have characteristically low electron affinities compared to 4A elements. And then the rest of these trends just follow the idea that electron affinity increases as you move to the right across the periodic table. So the exceptions that you need to look out for are your 3A and 2A. So 5, 2, 3, and 1A elements. And we've discussed each of those exceptions in the previous sections of the notes. Does this example make sense to everyone so far? So adding some actual element symbols. So magnesium would have a lower electron affinity than aluminum, which would have a lower electron affinity than sodium, which would have a lower electron affinity than phosphorus, followed by sulfur, and then chlorine has the largest electron affinity. Any questions on this example? This is very similar to the type of questions that you'd be asked on an exam. I forgot to put silicon. Silicon is greater than phosphorus and after sulfur. There we go. So electron affinity is different than atomic radius. Yes, so in general, the trends for electron affinity are closely correlated with atomic radius, but there are exceptions. So phosphorus is an exception, magnesium is an exception, and sodium is an exception. In that case, these magnesium and phosphorus have characteristically small electron affinities as a result of having to either place electrons and pair electrons or place electrons in high energy p orbitals. As a result, our ordering is modified to account for these exceptions. Does that make sense? Okay, so let's now discuss this idea of successive electron affinity. Just like successive ionization, you can successively add electrons to an atom, and the electron affinity can be recorded for each subsequent ionization. So this would be the first electron affinity, this would be the second electron affinity. And in general, electron affinity will become very positive when you attempt to ionize a noble gas configuration. Further, electron affinity drops pretty dramatically as you attempt to add additional electrons to an atom. So that's why, interestingly enough, the first electron affinity for oxygen is negative, while the second electron affinity is positive. Any other questions on this example? Okay, so let's really start to apply what we've learned, and let's try to first arrange sodium, calcium, nitrogen, and oxygen in order of increasing ionization energy and increasing electron affinity. So let's spend about 4 to 5 minutes on this example, and then we'll discuss. I'd like to see some rankings in the chat, and if you have any questions, don't be shy to type them in the chat at this time. And we'll discuss this example in 4 to 5 minutes. And for ionization energy, just remember one of our exceptions, the 5A and 6A exception. And if you're wanting to compare multiple atoms, you may want to draw an orbital box diagram. And from there, it should help make things a little bit clear which atoms are relatively easy to ionize, which electrons are relatively easy to remove, and which electrons are difficult to remove. And we'll discuss this example in about 3 to 4 minutes. And let's try to get a few more proposed rankings in the chat for ionization energy and electron affinity. And the response I see in the chat for the ranking of each of these atoms in order of increasing ionization energy looks great so far. Let's keep working on this example and we'll discuss in about another 2 minutes. And we'll discuss in about another minute and a half. Let's try to get some responses for the electron affinity values for each of these 4 elements. And we'll discuss momentarily. And the ranking I see in the chat for the ionization energy looks great so far. Let's try to get some responses for the electron affinity. And the responses I see for the electron affinity look perfectly reasonable so far. Okay, so let's discuss this example. So for ionization energy, so we know that there's one major exception where 5A elements have a greater ionization energy than 6A elements. Again, what is the reason behind this? If we look at a 6A element, we notice that they have a set of paired electrons, and that paired electron is higher in energy and easier to ionize. So we have oxygen. So we have nitrogen greater than oxygen because oxygen is easier to ionize. And then calcium is greater than sodium, as ionization energy in general increases as you move to the right across the periodic table, with a few exceptions. Okay, so here's our first ranking. Now let's look at electron affinity. So electron affinity in general increases as you move to the right across the periodic table, but again, there are some exceptions. The 1A electron affinity is always greater than the 2A electron affinity, and that's because if we think about a 2A element, such as calcium, in order to add an electron, that added electron would have to go in a higher energy orbital. So then, calcium has a lower electron affinity than sodium. And now if we compare nitrogen and oxygen, a 5A element such as nitrogen has a lower electron affinity than oxygen. And the reason for that is that if we want to gain an electron, inherently we would have to pair our electrons. So then nitrogen has the next highest, followed by oxygen. So this is our ranking for these elements in order of increasing electron affinity, with oxygen having the largest electron affinity. Does this example make sense to everyone so far? So let's try to rank these elements finally in terms of atomic radius, just as a review and to make sure we're comfortable with these periodic trends. This is exactly how I'd format a question on the exam. I'd ask you to rank 4 elements in terms of electron affinity, ionization energy, and atomic radius. So let's take about 3 minutes and let's rank these 4 elements in order of increasing atomic radius. So looking at your question in the chat, so we have sodium, which is N equals 3, and calcium, which is N is equal to 4. So looking at, so just to go to the ionization energy table, just to provide you a little bit of so let's go all the way up to our ionization energy table. So if we compare sodium to, for example, calcium. Now, you are correct in that calcium has a larger orbital. And as a result, you would initially expect calcium to have a lower ionization energy. However, keep in mind that that generally holds true. However, if we think about sodium, for sodium, going from sodium to sodium plus, we are generating a noble gas configuration. We're going from neon 3s1 to neon. Well, if we go from calcium to calcium plus, we are going, from calcium to calcium plus, we're going from argon 4s2 to argon 4s1. So even though, so to answer your question in terms of ionization energy, so even though typically we'd expect the N equals 4 calcium to have a lower ionization energy, because when we ionize sodium, we're generating a noble gas configuration, it is especially easy. It is substantially more facile. It costs a substantially lower amount of energy to remove an electron from a 1A element than a 2A element, because you're generating a noble gas configuration, which is particularly stable. Does that make sense? And that also plays into why calcium has such a small electron affinity. Because not only do you have a large orbital, but if you do place your electron in that larger orbital, less stabilized by the nucleus, you will end up filling an empty high energy p orbital. So, but that is a very important observant point. On the exam, I won't have you as frequently compare across groups and periods, because the rules start to get a little bit more nuanced. So the reason for ionization energy, why oxygen has a lower ionization energy, as we discussed in our list of exceptions. So oxygen has a paired electron, and this paired electron is relatively easy to remove. Well, if we compare oxygen to nitrogen, nitrogen does not have a paired electron, so removing this unpaired electron is relatively difficult. So essentially, pairing raises the energy of your electron, makes it easier to remove. That's why oxygen is surprisingly easier to ionize and remove the first electron than nitrogen. Does that make sense? Perfect. Any other questions I can address? These have been great questions so far. Okay, so let's take a moment and let's rank each of our atoms in order of increasing atomic radius. And we'll spend about 2 to 3 minutes on this last example, keeping in mind that we noted that calcium is N equals 4, sodium is N equals 3, nitrogen is N equals 2, and oxygen is N is equal to 2. And we'll discuss this example in about 2 minutes. And we'll discuss this example in another minute. Let's get some rankings of each of these elements in order of increasing atomic radius. Okay, so let's discuss this example. So first and foremost, we sort based on increasing n. So oxygen and nitrogen are n equals 2. Sodium is n is 3. Calcium is n is equal to 4. Okay, now we look at the number of protons. Oxygen has a greater number of protons, so it has the smallest atomic radius. So here's our ranking for each of these 4 elements in order of increasing atomic radius. Any questions on these examples? Okay, so let's keep going now. And let's talk about general trends in chemical reactivity. Let's try to relate these ionization energy and electron affinity trends to trends in chemical reactivity. So first, 5A through 7A elements typically react to gain electrons to reach a noble gas configuration. And the reason for that is they have a relatively large effective nuclear charge, and they can accommodate gaining a negative charge more readily. Likewise, as the opposite example, a 1A or 3A element typically reacts to lose electrons to reach a noble gas configuration. Why? These outermost valence electrons are high in energy, and it is relatively easy to lose those valence electrons when your element has a low effective nuclear charge. Okay, so we're starting to correlate these trends in ionization energy and electron affinity to tangible patterns of reactivity that we've seen previously. Okay, so let's try to answer the question, why are group 1A to 3A elements great reducing agents? And I'd like you to tell me which metal would be a better reducing agent, lithium or cesium? And to give you a hint, reducing agents function by losing electrons. So your explanation should be based on what periodic property? What periodic property should be the basis for your explanation? Ionization energy, exactly right. So we'll discuss this example in about 3 minutes, and then let's try to get a few responses in the chat in the meantime. And we'll discuss this example in about another minute and a half. And I'd like to see a few responses in the chat in terms of what species, lithium or cesium, would function better as a reducing agent. Which species has the lower ionization energy? So your logic is correct, but I would look over and double check the trends in ionization energy to specify which species would function as a better reducing agent. Okay, so let's discuss this example. So group 1A through 3A elements are great reducing agents. Why? Because they have relatively small ionization energies, and they can readily donate electrons. It doesn't cost a lot of energy for these elements to donate electrons and function as reducing agents. So when I'm asking what metal is a better reducing agent, what I'm essentially asking is which metal has a lower ionization energy. So if we compare lithium, which is N equals 2, to cesium, which if we check our periodic table, cesium is an N equals 6. So which element, lithium or cesium, would have a smaller ionization energy? Cesium has a larger orbital than lithium. So which element has the smaller ionization energy? Which element has the smaller ionization energy and it functions more efficiently as a reducing agent? Let's try to get some responses in the chat. Which species has a lower ionization energy, lithium or cesium? Yep, so cesium has a lower ionization energy, ergo we'd expect cesium to be a better reducing agent, as there's a smaller energetic penalty for cesium to donate its electrons. Any questions on this example? If not, let's keep going. And let's try to focus on this next subject. And let's try to ask, why are group 5A through 8A elements great oxidizing agents? And I'd like you to tell me which halide is a better oxidizing agent, fluorine or bromine. And again, when we think about oxidizing agents, we're thinking about gaining electrons. So we should invoke what periodic trend? What periodic trend should we care about for oxidizing agents? What periodic trend should we care about for? We should care about electron affinity. Exactly right. Okay, so let's spend about 3 minutes on this example, and then we'll discuss. And let's try to get a few responses in the chat, and we'll discuss in about 1.5 to 2 minutes. And the responses I see in the chat look great so far, and we'll discuss in about another minute. Okay, so let's discuss this example. So 5A through 8A elements are great oxidizing agents, as those elements have large electron affinities. So if you're thinking about which halide is a better oxidizing agent, fluorine or bromine, we're comparing fluorine, which is N equals 2, to bromine, which is N equals 3. And we see that fluorine has a larger, fluorine has a larger electron affinity. So fluorine gas is a better oxidizing agent. We would expect that, at least. There's a little more nuance into this idea of oxidizing and reducing agents, but I found this is a great connection to this idea of periodic trends and reactivity. Any questions on this example? If not, let's keep going and let's talk about periodic trends in terms of metallic character. So you notice the metals occupy primarily the bottom left of the periodic table, while non-metals occupy the top right. Metals are ductile, shiny, and they typically like to lose electrons. Now, as you move down a column or group, your metallic character increases. That's why, for example, if we compare carbon and lead, lead has more metallic character. However, as you move right across a row, metallic character decreases. That's why lithium has more metallic character than nitrogen. So if I'm wanting to draw an arrow for metallic character, I would draw an arrow going down and to the left. So this is metallic character. I often like to summarize these rules in terms of arrows, as it makes it a little bit easier for me to remember these periodic trends. You can also know this intuitively by the fact that metals are primarily on the bottom left of the periodic table, and metals, by definition, exhibit more metallic character. However you want to think about it. Okay, so we've wrapped up this current chapter on periodic trends. We don't quite have enough time to start the next chapter in this lecture block. So what we're going to do is we're going to take a break, and then in laboratory, we're going to start the next chapter, which is the Lewis model of chemical bonding. So I'll be posting this recording